Hi, Assalamualaikum. So this is our third video. We will continue our lesson, okay, from the uh, previous slide. Okay, we will continue in terms of our discussion in terms of probability of arrival and departure. Okay, as we said earlier, assume a very small time interval of length h, and in this time interval, only one event happens, either an arrival or departure. Meaning departure means the customer is being served. Since the rate of arrival is lambda per unit time, then we can say that the rate of arrival per interval h is lambda h. The thing about this, let's say we have an arrival rate of lambda equal to 2% per second, then h is 5 per second, then arrival rate per second is 10. Okay, 5 multiplied by 2. Okay, you need to read yourself. I think you can read this. Probability of arrival and departure. We know the probability equation here. And here you can look little bit more yourself about the probability theory here. Okay. Probability of arrival and departure, since we assuming that h is very small, we can ignore the higher order terms because they become negligible. Okay. For example, 0.001, then h equal to h to the power of 2 become like this. Okay. H to the power of 2 become very small. Then we can ignore this. So we leave us with lambda h. So arrival, p arrival equal to lambda h. Similarly, we can show that the probability that a customer will leave the system, given that somebody is in the system is in the first place, is micro h. Okay, so departure micro h. So arrival is lambda h, departure is micro h. Okay, state or rate transition diagram for MM1. Consider MM1 system at steady state equilibrium. Such a system will have a variable number of customers. In particular, at any point of time, a customer may be added to the system through an arrival event, or customer may be removed from the system due to departure. Okay, so let's the example here describe that. Consider this system MM1 as a steady state. Okay, so at any time, at any point of time, one customer may be added or may arrive. Okay, may arrive into the system through arrival event, or at any point of time, any customer may be removed or finished or being served. Okay, or we could say that it is a departure event. The customer depart or finished or being served. So this is example of MM1 steady state. Okay, state rate transition diagram for MM1. Consider the state of system which exactly and customer are in the system. So you can read this. These are three ways which will result into the system moving into Sn. Okay, so you can read this. State rate transition diagram for MM1. The above diagram shows the transition. Solid arrow denote the transition that result into entering state Sn. This is solid arrow. Okay. As you may have noticed that we did not consider the possibility of arrival and departure happening in the same interval. Okay. From the above diagram, we can derive the following relationship. Okay. Probability of the system in a state Sn equal to probability that the system is in Sn minus 1 and one arrival happens, or probability that the system is in Sn plus 1 and one departure happens, or probability that the system is Sn and no arrival or departure happens. Okay. So if Sn minus 1 means one arrival happens, if plus 1, n plus 1 departure happens, or if Sn equal to no arrival or departure happens. So mathematically, we can write the above equation as like this. Psn lambda hash Psn minus 1 plus micro hash Psn plus 1 plus 1 minus lambda hash plus micro hash Psn. So this is equation 3. After rearranging terms, we get micro P Sn plus 1 equal to micro plus lambda P Sn minus lambda P Sn minus 1. So dividing by micron and substituting lambda over mu equal to P, we get this. P Sn plus 1 equal to 1 plus P, 1 plus rho lah ni. Because we already have P here, P Sn minus rho P Sn minus 1. Okay, state rate transition diagram for MM1. Okay, so you can read this. State rate transition diagram for MM1. You can see, now you can see how 1 plus rho 1 plus rho power of 2, rho to power of 3 plus is an infinite geometric series which will get reduced to 1 plus rho plus 1 rho power of 1 equal to 1 over 1 minus rho. Applying equation 5, we get this one. Substitute P as naught, result from the equation 6 back into equation 4, we get this one. Okay, equation 5, equation 6, equation 7. So this more complex equation coming. Now we are ready to compute the average number of customers in MM1 system. The total number of customers in the system can be given by the sum of the number of customers and their respective probability. Okay. Okay, you can read this. So average number of customers in MM1, we know that rho equal to lambda over micron. Substitute for rho, we get Q equal to rho 1 minus P more than lambda over micron minus lambda, equation 8. Average number of customer waiting for service, we know that Q equal to omega lambda W plus rho. Thus, solving this equation, we get rho square over 1 minus rho. Okay. Average time in MM1 system. Earlier, we saw that using Litter's formula, we can say Q equal to lambda TQ, which means TQ equal to Q over lambda. So, bigger than lambda over micron minus lambda multiply by or divide by lambda. So, we have 1 over micron minus lambda. Okay. So now we have a way to calculate the average time a customer waits in MM1 queuing system with infinite buffer. We could use this to figure out average delay. We could use this to calculate the average delay a packet may experience on a link by modeling a router and SMM1 queue. But the next question comes to mind that in the real world, we know that the router don't have infinite buffer. In this case, if one we could model routers with finite buffer queuing system here, where is the C and the length of the buffer, and derive the equation for getting an average time for an MM1C system. Okay, so next we will discuss about networks of MM1 queues. Assuming that we are modeling router as MM1 queuing system, we know that every router is connected to each other like tandem queues. Every router is connected to each other. Where traffic enters multiple queues, exit multiple queues, traffic streams merge or split repeatedly. This fact presents the challenge that once packet have passed the first MM1 queue, are their inter-arrivals still random on the next queue, or they become strongly correlated? Because if they are not random, any more than this will invalidate the queuing models based on Poisson arrival. Okay, this is the router networks of MM1 queues. Okay, we have here, so these queues going here, and this one going here, going here, going here, going here. Okay, so you need to be able to describe a little bit more on this figure. What are these? This router, multiple router MM1. So it turns out that somebody by the name of Lennox Kleinrock observed and resolved the problem by introducing the Kleinrock independent assumption. Turns out that by due to the effect of multiple stream merging and splitting at hops, it restores the randomness of inter-arrival property, therefore making assuming a Poisson arrival for packet as a valid assumption. So this guy observed and solved the problem by introducing Kleinrock independence assumption. So this assumption, we can assume Poisson arrival for the packets. So it become valid assumption. Okay. So we will discuss one example. Example. First, elaborate the use of benefit of queue theory in the data network. B, explain the network with notation MM1. What will happen to this system? Utilization factor rho more than 1. Okay, this is about column. Let's say you have a rate of user request for data is 12 requests per hour. On the server, one of the server can serve user at the rate of 1 request every 4 minutes. So how many requests per hour? Assuming the arrival of data uploading request follows Poisson distribution and service to request follows an exponential distribution. Okay, so C, first determine the utilization factor and system stability. Will the system can cater the request of the students? Second, find the number of users requests in the waiting line for data uploading. And thirdly, find the waiting time to successfully upload data in Column server. Okay, so these are the solution for this example. You can read yourself. So queue theory is to handle the buffer management in network device such as switches, routers. So it needs to minimize congestion and packet loss. MM1, first in, first out single server system, Poisson inter-arrival with exponential service time based on Markov birth test process, infinite buffer waiting room, infinite population solution. Model should be used, MM1 QE model, the average rate of request arrival, lambda 12 per hour given, the average rate of serving request, micron, 1 in 4 minutes or 15 per hour. So you need to convert this, 1 in 4 minutes given, so you convert into 15 per hour. So the utilization factor P or rho is lambda over micron. So this is less than 1. System is stable. Number 2, number of requests in the server. Number of requests else equal to lambda micron minus lambda equal to 4. So lambda is 15 over 15. This is 12 over, this is 12 over micron is 15 over 12 equal to 12 over 3 4. Okay, number of requests waiting in the server, LQ lambda square micron minus, so this is 12 square micron 15 minus 12 1/4 over 15 jarak dengan 3 prima, so become 3.2. Waiting time, expected waiting time is 1 over micron minus lambda equal to 1 over 12 minus, sorry, this is 15 minus 12. Oh, 1 over, this is micron is 15 minus 12. 1 over 3. So why we can 0.27? So you need to check this one. Okay, that's all for today. I think I'm tired already, so I will check for you the answer for this. So you might check yourself, 0.267 hours, because the calculation just now is 0.33. 1 over 3 is 0.33 hours. Okay, so we will continue in the next video for topic 1.3, application of the QE models and strategies. So that's all for now, for today. Hopefully everybody is okay. I will provide you with the attendance record. So once you watch any video in YouTube asynchronously, you study on your own pace, on your own time, so you need to record your study. You need to record as attendance, or I will provide the link for the asynchronous class attendance. Okay, that's all. Thank you very much. Hopefully you will understand a little bit about this topic. This is our first chapter. Don't worry if you can't really understand about the subject. Still more to come. That's all. Thank you very much. Bye bye.